Hi everyone, today we have a nice discussion about RoseTTAFold All-Atom, long-awaited and apparently soon to come out. And we'll also talk a little bit about AlphaFold All-Atom. So let's go with that and have a nice discussion with Rohith.
Before I start with all the details, this is the work of a lot of different people. So I want to recognize all these people, and it's much harder to recognize everyone with just their name, but putting a face to a name is always great. So yeah, before we get started, this is just a big collaborative effort, and it's been very exciting to be able to work with all these people and learn from all these people. So the ideas that I'm going to talk about today are split into two categories, right? The first is structure prediction, and the second is backbone generation, right? So structure prediction, most people are probably familiar with, is this idea of taking an amino acid sequence and predicting a 3D structure. Backbone generation, people are probably also familiar with in protein design, which is taking some sort of corrupted structure and then recapitulating the 3D structure. And so that could be fully corrupted, and then you're making unconditional samples of protein structure, or it could be partially corrupted, and then you're making some sort of conditional sample of protein structure or a protein backbone given some conditional information. And so the kind of idea that we were thinking about is how do we do this like conditional sampling with non-protein biomolecules? So the way that we were thinking about this is, can we design a neural network architecture that models all these different molecules in the PDB? And this includes proteins, this includes nucleic acids, this includes metal ions, small molecules, covalently modified residues, and one way to get pretty good intuition on why this is necessary is if you try to use RF diffusion to make interactions with non-protein biomolecules. So this is work from Woody Ahern in his previous paper, but he basically tried to do motif scaffolding of small molecule or enzyme active sites. And he found that, in many of the samples, you either have this pathology where there's no pocket or there's clashes, and really explicitly modeling these small molecules so the network knows that there's some space, some chemical in that space should resolve both of these kind of failure modes.
Rohith,
Mm-hmm.
on this slide now,
Yeah.
what did we do there? Like we have some scaffolds for, oh no, we have some binding site that binds a small molecule. We know that already. We want to improve its binding of the small molecule. So now we take the binding site. We don't change the binding site. We conditioned on that binding site, we this motif, we generate a backbone as a scaffold, and then we take the whole thing, run protein MPN, and get our new residues, and then see when we fold it, then the pocket is like gone and clashes with the ligand out there.
Yeah, so something very similar to what you just said.
Okay.
I think these actually are just the initial outputs from the like diffusion model, right? So it's
Ah,
like basically you take like these three residues, they're super important to catalyze this reaction or whatever, right? You give those as conditional information to the model, and then you generate like 1,000 backbones or something, right, with that, and then you just go through them and see like which ones would be good candidates to continue. And you see a lot of them have like these pathologies that you wouldn't want in something that you would test in the lab, for example.
yeah, sounds reasonable.
Cool. So but in protein design, we really want these interactions with these other molecules, right? So this up here is an example of an enzyme design problem. This is like a small molecule binding problem. And this one on the right is this like design of, this artificial photosynthesis system. And these are all like really cool applications where, you need interactions with non-protein biomolecules to satisfy the protein design objectives. Right. So, and I'm not going to go through the details, but the way we thought about this is that if we can create a good structure prediction model, as we've seen with RF diffusion, we can fine tune that into a good backbone generation model as well. So the first kind of step to this project was, how do we create a structure prediction model that can model all these molecules. And so there's a couple ways you could think about it, right? The first way you could think about creating a structure prediction model is something that models all the atoms, right? So you have like a full atomic representation, either like, you know, you might be thinking about it as a neural network, but you could also think like energy functions, right? That parameterize pairwise interactions between atoms. The second way you could think about it is, you know, some sort of sequential modeling. Like first you model the protein and then you model in the small molecule or atom or element or whatever, or metal ion or whatever you may desire. And then the last thing is kind of what we thought would be most impactful for protein design, where you do it both simultaneously. So you both sample the degrees of freedom of the small molecule and the protein together. So now we've kind of reposed the same structure prediction task that we discussed before, right? Where instead of going from just an amino acid sequence to a 3D structure, you go with an amino acid sequence and a chemical structure, some sort of information about atoms and bond geometry, to a 3D structure with the ligand bound as well. And so now you can imagine you have training data with residues from proteins and nucleic acids and atoms with these small molecules and post-translational modifications. And you can kind of model all these things that we set out to model in the like first or second slide that I showed. And so now, like, if you can also think about reposing this backbone generation problem, right? So in addition to being able to do structure prediction with an amino acid sequence and a chemical structure, you can also do backbone generation with a corrupted structure with the ligand, and then decorrupt it into a 3D structure with the ligand. And so first, I'm going to talk a little bit about the structure prediction element of this. And so we started with RoseTTAFold, which our lab had made in-house. And RoseTTAFold has this 3-track architecture. So it's very similar to AlphaFold, if you're familiar with that, where you have 1D information, 2D information, but in the case of RoseTTAFold, also 3D information. And these all interact with each other through these like biased axial attention operators and aggregate over, you know, the model can reason over both sequence, pairwise token information, and structural information. So what we did is, you know, we added DNA, RNA, and atom tokens to the sequence representation. We added the information about bonds to the 2D representation, right? We defined losses that operate on coordinate frames of small molecules in addition to proteins. We made sure the structure module updates the small molecule atom positions as well. And we added in these chirality inputs so that the structure obeyed. So at input time, if you only have the 2D bond graph, you don't know what the chirality of a given chiral center is. But so we added in basically inputs that define that. And so in practice, it looks something a little bit more like this, right? So you have your sequence inputs and your molecular inputs, and the sequence, the element types are kind of concatenated to the query sequence of your protein. And if you don't, I mean, you can also not have elements or not have a query sequence, you know, and then, you know, these homologous sequences through the MSA are provided as well. And then the bonds are provided as this like 2D pair bias. So you could imagine like this oxygen is double bonded to this carbon, as you can see here. So you get like a 2 for a double bond. And likewise for chirality, you have, you know, this chiral center, and then you get an order of atoms and whether the angles formed between those atoms are positive or negative. And yeah, I can talk more about, you know, any of these things if people are interested. I kind of skipped over all of this pretty quickly, but yeah, like maybe now is like a good time to stop and see if anyone wanted to talk about any of these things.
Yeah, maybe I think an interesting question would be like, right, you use SC3, no, what's it called? SC3 transform?
SC3 transformer, yeah.
Yeah. Do you think that's important for handling the ligand atoms, right, where we now no longer have, or do you think this type of network is important for handling small molecules compared to handling residues? And I mean, in AlphaFold, we've seen that it's not really necessary, and you can have just this what do they call it? Yeah, you can just have
Invariant point attention, right? I think.
yeah. So your take?
My general opinion on this is that there are probably many different architectures that you could use in that 3D track, right? I think like we had experimented a lot with the SC3 transformer and doing different things with that. So that's kind of the route that we went. But my guess is that, you know, there's many different ways that you could, I mean, you could probably repurpose the invariant point attention for these things as well. Like it would just be some figuring out.
Okay, and then can I use like your model? Do I always have to include some protein input, or could I now also just, I don't know, fold some DNA or whatever?
Yeah, you can do that as well. We
Okay.
never showed like DNA only training examples. So your results might vary. We showed like RNA only training examples. And then we also showed small molecule only training examples. So I think like those would be cases where you'd have better likelihood of success in using the model. But yeah, you don't need to provide protein input.
Yeah. And then Shilpa is asking in chat, do you or can you explain a little bit how this 3D track works? Or what are the features in the 3D track?
Yeah. So the 3D track, so it basically just takes the information from the 1D and 2D tracks, and then it creates this graph, and then someone else can probably explain how like these SC3 equivariant networks work better than me, but basically like it takes the distances from the previous iteration of the network, and then it makes this basis function that it like embeds the features into to maintain equivariance. And the only additional features that we provide to this network is for chirality. We provide the gradient of, actually, I can probably just show this a slide that explains this reasonably. But so basically for chiral centers, there's a bunch of angles that you can compute between planes in a tetrahedron, right? And so depending on whether a chiral center is, positive or negative in this case, you'll get different angles. And so we provide the gradient of those angles, the error of those angles from the ideal angles as this like L1 input feature, which is like a force. So it'll say like, oh, this atom needs to move in this direction with respect to the chiral center. I don't know if that is helpful, but that's kind of the features that we provide to the SC3 network.
And
then
how
go ahead.
How do you provide templates? Like, can the templates also include glycans or something like that?
So yeah, we don't provide like those types of templates in training. My guess is that you would have to do that in training to get like meaningful results at inference time. But yeah, that's definitely something that you could train, I think.
Okay, and how are the templates included at all? Like, how does the attention to the templates work, so to say?
Yeah, the templates are included. Basically, there's two ways that they kind of get included. The first way is that the pairwise distances of the templates and the sequence of the templates get embedded in like basically in basically exactly the way that like the 2D information gets embedded, right? So it's like using this like axial attention, right? And then also the first template, which is arbitrary, is provided as the initial template coordinates, right? As the initial 3D coordinates. So instead of starting every time from like a black hole initialization, you start from like some arbitrary template information. So the first 3D update, the distances aren't are not always zero. They might have some information from the template information.
Okay, and then how do you make sure that the template has the right size?
Oh yeah, you do a sequence align. You align the template sequence against the query sequence, and then like only the positions that aligned get included. And then there's like a feature basically that indicates whether two pairs of distances should not be considered in the template. Yeah, if that makes sense.
Okay. And what are the coordinates of the gaps, so to say?
Those get initialized to like the nearest resolved, the nearest non. So like yeah, when you provide, this is all like super in the weeds, but like when you provide the template in the 3D input, the coordinates of things that are gaps are initialized to the closest non-gap residue.
Okay. And then right for your torch no cahedral center stuff, um, you provide these gradients as inputs to the neural network. Did I get that right?
Correct.
Yeah. So that's kind of interesting, right? That you yeah, you don't apply the gradients as to the geometry. You know, you feed them as input to the network and let the network does itself figure out what to do with them, and itself can decide whether to update according to them, so to say, or to ignore them.
Yep.
Okay, but then do we have some results for the stuff, or what are we getting to now?
Yeah. So the next thing that I was going to talk about is another training kind of augmentation. So one of the things that we do, which I guess is similar to some of the stuff that you've also been playing around with, is atomizing certain regions of proteins. So taking random contiguous chunks of protein and converting its representation from the residue representation into the atom representation, right? And then you lose all of the like multiple sequence alignment or template information for these cases, and it looks something like this, right? So your cartoon view is the things that are in residues, and then the like line and stick view are the things that are as atoms, right? And so now the network has to learn how does it update these atoms to fit into the way that the residue representation was folded, right? And this is also enables the prediction of these covalent modifications, right? So what you can do is you can atomize a residue that has a covalent modification, and then you draw an explicit covalent bond in that pair bond bias that that connects the modification to the residue. And then you have to update the chirality information, and then you can indicate where this residue is in the polypeptide sequence, right? So then now you have a pretty nice way to represent these covalent modifications, which was kind of the last thing in that list of types of molecules that we wanted to represent.
Okay, so but the idea with this data augmentation is basically we no longer, we augment our data by, right? We want our network to understand how does this residue interact with this small molecule. And now we have lots of data with small molecules interacting with a protein, but we can get a lot more data like this to train if we take a residue and yeah, just pretend it was a ligand and say that this small ligand is bound by all the residues surrounding it, and then the network can learn like the interactions with that ligand. And yeah, I mean, I also did that in my stuff, right? And for me, the inspiration there came from the group of Nicolas Polizzi, right, who has this Vandermeer paper where they argue that the interactions of ligands with side chains are very similar to the interactions of side chains with side chains. So you go ahead and pretend that a side chain is a ligand and you train with that.
Yeah. It was neat to see that you guys had tried something very similar. I actually hadn't. The way we got to doing this was not from reading that paper, so it was also very interesting to see the intuition from that paper as well. After reading your paper, so yeah, that was very interesting to see, like, coming to the same place from different directions.
All right.
Cool. So the last thing is quickly talking about like the loss function that we use for structure prediction, right? And so in the AlphaFold paper, right, they introduced the frame line point error, which is just this idea of you take these NC alpha C frames, and then you take the predicted and the true frame, you align them, and then you take the error over all other atoms. And this had worked really well for us in RoseTTAFold as well. So we thought a nice way to extend this to ligands would just to be to do something very similar, where you take a defined triplet of atoms for each atom in the small molecule. You take a defined triplet of atoms, and then you take the error over all the other atoms. So that was the main loss function that we used to supervise this network. And so now I'll quickly go through some of the structure prediction results. I'm trying to be cognizant of time to get to some of the design results as well, so I'll speed through these. But the first thing we want to see is, do we ruin the monomer prediction accuracy of the network, right? Like, are we still able to predict monomers with high accuracy? And these are a bunch of CASP targets from a couple of years ago, and we end up doing pretty well on all of these.
Wait.
Yeah.
Let's not speed through the
Okay.
yeah. And,
Yeah.
so what are we looking at here? We have some cast whatever predict targets, and then each dot here is one of those targets, and we're showing the I think
GDT.
TM score.
GDTS score. Yeah. Sorry. Yeah, I can explain about
GDTS for RFAA and for AF2, and we see it's kind of the same.
Yeah. And yeah, this plot on the right is the same thing for RoseTTAFold 2, right? Which is like the updated RoseTTAFold algorithm, and it also seems to match pretty well.
Good.
Yeah. So the first kind of sanity check is that we didn't break anything.
And now, what would you complain about here as the skeptic? Like, CASP is so similar to all of these CASP targets were so similar to all of the training data. I would be much more interested in results on this and that. Like, what would you say are the caveats here, if there are any?
Yeah, I think that in general is a difficult thing for these types of methods, right? Where like AlphaFold presumably is trained on a different subset of the PDB than RoseTTAFold, right? And like, so finding things that are not in their training set and not in our training set is like non-trivial, at least to me. I don't have a great sense of how to do that. And so these kind of like things like CAST, which are like, blind assessments, I think are like kind of the thing that we've been using for these types of comparisons, right? But yeah, there's probably like an ideal world where there's like, a benchmark that's doesn't have sequence overlap with anybody's training set. And yeah.
Okay, so you don't have any other results than this?
On monomers, no. Yeah, it's
then the next set is for DNA, RNA.
Yeah, I didn't put in the DNA RNA results. Basically, the plots look very similar, where we compare to RF2 nucleic acid, right? And it performs very similarly to those. Yeah.
The
next thing,
want to show?
Huh?
What else did you want to show?
Oh, yeah. So the next thing I want to show was these predictions of small molecule complexes. So these, in our case, are things that have low sequence similarity and low Tanimoto score to things in our training set specifically, right? And so, you know, and we do worse on cases without high similarity to our training set, but there are some cases that we are able to predict well still. So there's some, it's learning some features about the distribution that are useful for these predictions in general, even when they're not very similar to our training set.
Okay.
And then I want to get
the not similar to the training set in what way? Not similar?
Yeah. So the definitions that we used are 30% sequence similarity to any training structure and 0.5 Tanimoto similarity to any small molecule in the training set. So
Okay.
yeah, obviously there's like more and less rigorous ways to do it, but I think in general, just like mostly as a sanity check, if nothing else, to know that like, you know, that we are able to make these types of predictions. Yeah.
Yeah, I mean this I maybe don't see the big thing here, the docking or so. I see like the binding site design or binder design as
Yeah.
the cool thing.
Yeah.
But
I agree as well.
what do you think about the like AlphaFold All-Atom results on the Postbusters dataset, I think, where they get like 74% RMSD below 2, and while DiffDoc gets like 38% RMSD below 2, and you get 42% RMSD below 2.
Yeah, I mean, I think it's really exciting. And I think, you know, it's like one of those times in this field where it moves really fast and there are a lot of good ideas out there, right? And I think it's like one of those exciting times that you get reminded that there are more good ideas to explore. And yeah, it's definitely worth continuing to explore them. Yeah, that's kind of how
Yeah,
I interpret those.
but probably, or yeah, I would speculate that will at least be some time until we get to see any AlphaFold code or we can use the stuff. So can we use your stuff sometime soon?
Yeah, yeah, very, very soon. Yeah. I've been working on creating, so like there's, you know, a lot of different like you mentioned earlier, you know, you can have RNA only and or DNA only, and we kind of handle this in multiple separate pipelines. So now I've been merging everything together so that there's one elegant way that we can use all of the features. And yeah, I don't have the exact date for you, but yeah, it's in very near future. Yeah.
So it's like months or weeks.
Uh, I would say like within a month is my like goal. I would before the holiday season is my goal. Yeah.
Okay. Oh,
Yeah.
nice, nice. So this year. So,
This yeah, that's like I said, that's my goal. Obviously, like if there's still some small bugs and things that need to be fixed, I don't want to over promise, but yeah, that's the general goal for me personally, not set by anybody else. Yeah.
yeah. Cool. Very nice.
Yep.
Um, that's a clear advantage over AlphaFold AA. But yeah, then what's
So the
next?
other nice thing is you can kind of mix these things together, right? You can do protein and DNA and small molecule and metal ion, right? And like it's not to say that you're going to get these right in all cases, but just that the model is able to represent these kind of more complex relationships. And like, you know, downstream when we're doing protein design, we can start to also think about these types of things. And we don't have any results of these types of things in this paper, but, you know, just that this is kind of like a possibility. And the other thing that's nice is, like I said earlier, is we can represent these covalently modified structures, right? And so, and there's, you know, this also has some similar properties of depending on how low in sequence similarity you are to the training set, you get different performance. And depending on, and surprisingly, kind of independent of what type of modification it is, you get reasonably good performance. So we were very excited about this in general, especially, you know, there's a lot of applications in protein design as well where you get to use this. So on the y-axis here is the LDDT interaction. So just how many pairwise distances are, you know, within a low error to the true distances. And on the x-axis here is the most similar sequence in training. And yeah, there are still many accurate predictions made in the like 0 to 25% regime. And then here, you know, it's the same y-axis of LDT of interaction. And on the x-axis is, you know, like different types of modifications. So glycosylations, or, you know, there are many enzymes that covalent, or enzyme cofactors that covalently modify proteins for their reactions. And then there's many others that are things like drugs that covalently modify, or these like other molecules that seem to be like scaffolds and things like that. And so, and then these are a couple example of, you know, predicted glycans. And, you know, as you'd expect, like as you're closer to the base of the protein, you end up getting more accurate predictions. And then, but you see pretty good accuracy across the chains in general. And
Very
so
nice.
now, sorry?
Sorry, just go on.
Oh, yeah, yeah. So now I want to talk about backbone generation. So the whole motivation behind doing this was like, can we create a network that we can generate new proteins that interact with small molecules? And so, as I said earlier, you know, you have a corrupted structure with a ligand, and you want to denoise that and make a 3D structure with a ligand. And so as many work in this field has been doing, we use this like diffusion process, right? So this top image is how it would work with images, right? So you start with this image of a cat. This is from like the an NVIDIA blog post, and you slowly denoise it into Gaussian noise. And then you learn a network that denoises this. And this is a figure from the RF diffusion paper, where it shows the application of this to proteins. And so in this case, proteins have two elements that can be noised. One is the absolute position of the C alpha, and then the other is the orientation of the NC alpha C frame, right? And so these are jointly noised in a forward process. So you start from a protein structure, and then you create some sort of Gaussian noise, and then you learn to reverse that. Did you have a question?
Yeah, like did you also try making, right? Now you start from this this template initialization thing, so to say. Did you also try something like maybe making your like just your structure prediction module, making that a generative model?
No, we didn't try that. We've discussed doing that. Yeah, inspired by some of your work as well. But we haven't tried that yet, at least. Yeah.
Yeah, I think it would kind of be cool to like either, or yeah, maybe you have a diffusion model as your generative model, or you could do like flow matching from your weird template initialization to the actual structure, and maybe that, yeah, maybe that works nicely. I'm not sure, but then here in your diffusion model,
Mhm.
what initialization do you use? Like you don't do anything with templates anymore, right? And what am I
So
what am I
basically, the template is used as this self-conditioning input. So
uh,
the prediction of X naught of the previous iteration is provided as the template, and then the X naught, like the not the X naught, the XT information. So like what is the noise at this step is provided in the coordinate information. So yeah, I don't know if that, yeah, I don't have
yeah,
a slide explaining that, but that's like the two pieces of information that go through the network and how they do so.
sounds good.
Cool. Um, so basically the idea was that we kind of left the methodology of RF diffusion unchanged. So we did something very, very similar. And what you get, right, is a model that can denoise the backbone coordinates in the presence of the small molecule. And in this case, we don't apply any noise to the small molecule. The small molecule is always given as like motif fixed input, right? And then we just resample, or we just sample all the backbones around this small molecule. And this is like one example of a sampled backbone. And then as you mentioned earlier, we fit a sequence to it using an updated version of protein MPNN that can also handle these atomic contexts. And then we refold it with AlphaFold to see whether we can, recapitulate the same structure. And so the bottom panels here are doing that exact experiment, right? So first you use RF diffusion and you just add this attractive repulsive potential that tells the model to not overlap with the molecule wherever it is, right? The second here is using RFdiffusion All-Atom, right? And then the third is using RFdiffusion All-Atom and just adding a simple attractive potential just to say, make the protein go around the ligand. And
wait a second, Rohith, then
yeah.
Proportion here means the proportion of correctly refolded structures where, I don't know, the TM score is below, above, blah, blah.
Yeah. So the proportion here is the proportion of, this is a continuous density function, right? So it's like the proportion of things with AlphaFold RMSD less than like, zero, in this case, zero, in this case, probably one, here, 2, 4, et cetera, et cetera. So the cutoff that we normally use is 2. So things with RMSD less than 2 from the predicted backbone, right? And, oh, shoot. And so the values here shown are the fraction of cases that have under 2 angstrom RMSD to the backbone. And so in pretty much all of these are 4 benchmarking cases that we chose. In pretty much all of these cases, the fraction RMSD was much higher, or was higher than the fraction RMSD less than for the RF diffusion with just the attractive repulsive potential. But the interesting thing we found was that if you measure the Rosetta energies of these output structures, the RF diffusion outputs had really bad or really high energies, right? And so we have our hypothesis is that, when you use RFdiffusionAA, which is aware of the small molecule, the network has the ability to make favorable interactions that or position the backbone in ways that could make favorable interactions with the small molecule. And then in when you actually create these, when you actually score these with Rosetta, there are a lot more, per se, hydrogen bonds, or there's a lot better shape complementarity with the actual molecule, and the scores become much lower. So this was,
I mean, this is now in this one, right? What are the 4 columns for?
Yeah. So the 4 columns are 4 different benchmarking cases. So the first 2 benchmarking cases are in the training set, and the second 2 benchmarking cases are ligands that have like lower than 0.5 similarity to any ligand in the training set, right? And so it's just to illustrate that the network.
Okay. Then my conclusion sort of wouldn't be that using this attractive potential results in us having much better Rosetta delta G's. It would be more like, either you use the attractive repulsive potential and then your results are worse, or you use the attractive potential and then your results are kind of the same or worse in terms of RMSD. So don't bother with this potential stuff and just use RF diffusion AA without any of this potential stuff. So wrong?
I think it's a little bit complicated, right? Because I think in most cases using RF diffusion AA without the potential is the way to go, right? There might be some cases where you get like slightly better Rosetta energies, and it depends on how much you stock up to that being a good feature or not, right? But in most cases, actually, you don't even get better Rosetta energies either from using the potential. This is just showing that the previous method, which was like using RF diffusion, like really would not have been able to give viable solutions to these problems.
Okay.
So then we kind of took this into the lab, and so we decided to design against a bunch of different targets. The first one we chose was digoxigenin, which is a target that the Baker Lab had looked at previously with like scaffold-based design. And so here the input is just the small molecule, right? And then the whole protein backbone is diffused. And here's like a zoom in of the binding pocket. And, you know, when you do the binding assays, it binds very tightly. The protein's also extremely stable, so up to 95 degrees Celsius. And so these two values here this is the TM score against all ligands and are all proteins in the training set. And then this one is the TM score, the highest TM score of a protein that bound a molecule with greater than 0.5 Tanimoto to digoxigenin. So in both cases, it seems to be not very similar to previous, at least, you know, steroid kind of binding proteins. The second kind of challenge that we went after was binding heme with this like axial substrate. So like previously, Indrek in the lab had found that if you design heme with like an open pocket substrate, you can easily engineer it into an enzyme. Right. So he went out to design a bunch of different proteins that had, you know, a heme. This is like a one residue cysteine that coordinates that heme. And then this like placeholder molecule, like this molecule isn't meant to be the actual substrate, but, you know, it's just a molecule that takes up some space that is where the substrate would go. And this is kind of like an output, and he's generated a bunch of these, and he's experimentally verified a lot of these. And this is also very satisfying that the similar molecules in the PDB are actually quite different. At least, you know, there could be classified as the same fold, but on that kind of threshold. And, you know, when you test these in the lab, this is the wavelength that you would expect cysteine coordinated heme to absorb at, and you get a really nice peak. And when you knock that cysteine out into an alanine, that peak goes away, and it matches the spectra of just having heme unbound, which is what you would expect by knocking that out. So this is really promising that, you know, we have very specific heme. It's through the designed cysteine that we'd wanted, and the binding of this heme is also apparent at high temperatures. So we brought this up all the way to 90 degrees Celsius, and you see this peak is still very prominent. So this is really exciting to have these like super thermostable heme binding scaffolds that have these like space for these axial substrates. And yeah, future work could definitely do a lot of cool stuff with these, I think. And the last design challenge that we went after is designing these bilin binding proteins. So in this case, bilin covalently modifies a cysteine on the protein. And there's this autocatalytic motif. So these residues aren't meant to be binding the bilin as much as autocatalytic for the to allow the binding to happen. And likewise, you see in all these cases, you know, the TM scores against everything in the PDB and the TM scores against similar molecules in the PDB, and they all have, you know, slightly different topologies and binding modes. And the cool thing is they also have absorbance at different wavelengths. So basically, each one absorbs at a slightly different wavelength, which is indicative that we bound the bilin in slightly different ways, at least ostensibly. So this is also a very exciting result. So we're very excited, you know, of creating both RFAA and RFdiffusionAA, which, you know, have this ability to model all these new molecules and really open up different things we can do with protein design. And yeah, are there any other questions?
Yeah, why do I even want to design binders? Like, what's the purpose of the small molecule binder design?
Yeah, so I think like, so for example, for digoxigenin, right? I think there's like these diagnostic applications, right? Like, and the other application is like some of these drugs are toxic, right? So you might want to have a protein that sequesters that drug or like knocks it out if it's causing toxicity. For heme, you know, there's a lot of different enzymatic reactions that you could evolve this scaffold to do, right? There's like a lot of work showing taking like native heme binding scaffolds and evolving them to do a bunch of different reactions. And, you know, for bilin, it's really like bilin's a part of this like photosynthesis process, right? And so creating either like more stable or photosynthesis that absorbs at different wavelengths or things like that, you know, could have major applications. So there are a lot of applications of, you know, that require small molecule binding.
Okay. And right, you have a single 3D structure of a small molecule, and for that you design the binder.
Correct.
And in your binding design stuff that you did here, did you like take only like what was the 3D structure of the ligand that you took as input? Here, for example.
So so in different cases we did different things. In some cases we you know, used something like RDKit and made like, you know, X amount of conformers and then, you know, just generated them. In other cases, you know, we like for example in the heme case, we knew like how exactly we wanted the molecule to be positioned, right? So that you could optimize the like space for the substrate molecule. So it's based on like, you know, understanding of the design challenge.
Okay. And then Michael Heinzinger is asking, how do you combine or concatenate the 2D molecular, small molecule inputs and the 2D protein inputs? Like in one we have the bond flags and in the other we have the distances. How do you combine them?
Yeah. So basically the relative positional encoding is done separately, right? So like your I think that's your question, right? It's like in proteins you could imagine having like residue I and J and what their distance and sequence space is. So that's one embedding. Like given a residue I and J, what is their sequence distance? And then there's another embedding which provides the information of like atom I and atom J, are they bonded? Like what is the like either the bond distance, like how many bonds would I have to travel to get them, or what is the bond type between them? Yeah, those are all three different embeddings.
I think there was a misunderstanding, which I now also had, that the at these edge features, no, you're in your 2D track, you do not include any 3D distances, right?
What do you mean by 3D distances?
Euclidean distance.
You have like include as input features?
No, I mean, you have as edge features your radial basis embeddings of the distance between residue I and residue J, but that's only the case in the 3D track, right? And in the 2D track, we don't have any distance features like that.
So in the 2D track, there's like this biased axial attention, which takes the distances from the previous iteration of the 3D track and then embeds them and then biases the attention maps using them. So I don't know if that's your question, but there is bias from the coordinates in the 2D track.
Okay, so they are included in that way. But now I was asking this way because Michael Heinzinger's question is about you have in the 2D track like edge features corresponding to what type of edge you have, to what type of bond you have. And he was asking, how do you combine those edge features with the distance edge features? But those distance edge features are included in the 3D track as far as I understand, right?
Yeah, correct. Yeah.
Good. I don't know. Then can we maybe scroll back a bit through your binder design slides and do you have an idea what could be other applications of this model now besides we have a 3D structure of a small molecule, we want to design a binder method. Could there be any applications to doing something like generating small molecules as well?
Yeah, that's an interesting question. I think I've thought about this a little bit. Like, I think like one of the difficulties of generating small molecules is for proteins, we have this like very beautiful thing, protein MPNN, right? Where like we can mask all the residue identities and then just recover them later. I think for generating small molecules, you probably need to jointly generate the 3D coordinates and the element types, right? At least to some extent, because I'm not, at least to me, I don't have a clear idea of uh, how you would decode the atom identities of the molecules after you generated the 3D coordinates. I don't know. Do you have any ideas on how to do that?
I mean, you could do something similar to um, what's the thing called? So to ligand MPNN, but I don't think that makes much sense, right? And if you more or less the most atom types are already determined by where you put the atom, but I guess that raises the other question of why don't you generate the residue types and the amino acid positions jointly and instead do this two-step approach?
Yeah, I think at least in our hands and practice, it doesn't seem to be necessary, right? Like we've in most of the design cases that we've tried, at least so far, like doing the two-step approach seems to work. But yeah, maybe there are some cases that at least I haven't been exposed to yet where you do need to do them jointly. I feel like for small molecule design, that's like one of the cases where that would probably be true. At least that's my naive impression.
Okay, but you say now it's not necessary, then it sounds like, yeah, perfect. RF diffusion or RFAA diffusion works super well, perfectly. The problem is solved. And we don't need to improve the method anymore. Like, is
Well,
that
I think that there's like the way things work, at least to me, is you you try some problems, you see like you see what works and what doesn't work, right? And then you see that now we've gotten a couple of these problems to work, right? And then it's like we'll try some more problems and see which ones does it not work on, right? And then I mean there's definitely a lot of problems that this network would not work well on, right? And uh but yeah, it's a matter of, I think from my end at least, it's like how do we find the design challenges that are still difficult and then improve the methods further, right?
okay? Then we have in the chat. Mm, let me just read this quickly for the. Um, yeah, maybe this is an interesting question. How correlated do you find the RF or your Rosetta energy to be with binding design success or with binding affinity if you evaluate that in the lab? Do you evaluate that in the lab, binding affinity?
um Yeah, for some cases it's possible. Like for example, in this case on the screen, you can find the binding affinity. And but by Rosetta energy, do you mean like the physics, like the Rosetta energy scores?
Yeah.
Yeah. Yeah, I think there's some weak correlation between Rosetta energy scores and binding affinity. I don't think it's not going to tell you exactly what is the strongest binding, but
I
if
mean, do
things
you
are,
use the Rosetta energy for filtering your designs or something like that, or does it correlate a lot with design success?
yeah, I think again, it's like case dependent, like different binding targets, people will like use different filters. For example, for digoxigenin, like using Rosetta energy seems to be a reasonable filter. But I think it's like for the small molecule cases, it's really, really case dependent, I think.
Okay. Then how is RFAA better at generating enzymatic scaffolds based on a substrate molecule than previous versions of RF and RF diffusion?
Yeah, I think that like for enzymatic scaffolds, in a lot of cases, you have to have a substrate, right? So like if we go back to like, let's see, where did that slide go? To this slide, right? Like you would these would not be good like enzymes, right? But within the RFAA case, you can provide, this exact as input, right? So these three catalytic residues and this substrate molecule. And, there's probably more necessary to actually understand catalysis than just, some catalytic residues and the substrate molecule. But this is definitely one first step towards that. If you don't even model like this, it's probably going to be even more difficult to get an active enzyme.
Okay, have you already used RFAA diffusion for some enzyme design tasks?
Yeah, people in the lab have been trying this. So yeah, I don't have any results to report with you now, but definitely they will be coming in this soon.
Okay, sounds nice. Then can you elaborate more on atom frames? Like how do you do your fate loss? And how do you decide which way to point, basically? Which is your
Yeah.
first side atom?
Yeah. Basically, um, the way it works is that you take every atom, you enumerate. Actually, I probably just show a slide on this. Um, you so basically you take every atom, and each atom will have multiple like pairs of triplets of, or like it has multiple triplets of atoms that it's bonded to, right? And so the idea was just to pick one in a deterministic manner, or a relatively deterministic manner. So basically, you each, depending on the three atoms bonded, there's like a priority function, right? And like you choose for every atom what the highest priority frame that it exists in is. And then, yeah, if you enumerate through that process through all of this, you would get something like this. And so
Mm,
that's kind of the idea.
yeah, wait a second, wait a second. Then
Yeah.
Jody also asked about this guy here, for example. Like what distinguishes the triangle that you chose, right? You
Yeah.
chose this.
Yeah.
What distinguishes
Yeah.
that from the one, or what distinguishes that from this one?
Yeah. Yeah. So yeah. So you're right. That's why I said it's like a relatively deterministic process, right? It's not like fully determined in all cases. And there is some arbitrary way that those are chosen. And the hope is just that similar molecules are featurized in similar ways where that arbitrary distinction is similar, but it's not guaranteed to be true.
Okay, okay, but I mean, your choice here to go for this one is also
Hmm.
still arbitrary, but it's not random. So are you
Yeah.
saying that here it's just then random between these two?
Well, it's random in the sense that it picks like the first one per se, right? Like if it's enumerated all of them, it picks the first one. So if it
Oh,
enumerates them in the same order every time, it'll pick the first one every time, but it's not guaranteed to do so.
okay. Then force molecule. No, that's not interesting. Did you benchmark RFAA performance on single sequence input?
No.
No. Okay. Um, then yeah, are there results like why are you saying that this it's not necessary, right? The joint sequence structure design. Do you have some results where protein MPN or the two-step approach works equally as well as the joint design?
Uh, I guess I guess not really. Like I think that um I think it's more of like a question of like, can we solve the design challenges that we have, right? And it's like when people are trying design challenges, like often the feeling is not that the failure point is like the lack of joint sequence structure generation. I mean, it might be the case, but yeah, there's no like clear result comparing the two and dictating that one should be chosen over the other.
I mean, it could just be that the um like your average quality of the design that you get is just 10% better, right? And not, you don't unlock any new capabilities, but just because you do it jointly and your structure module can reason about the sequence that you design as well, it works a bit better and you have more reasonable designs.
Yeah, that definitely could be the case. Yeah.
And but wasn't there this protein generator paper,
Mhm.
and that was also from your group? And
Yeah.
yeah, why are people using RF diffusion and not protein generator?
Well, I think that they're designed for different cases, right? Like the like RF diffusion case is for like when you want to do like geometric like conditioning, right? Like in this case, we want to condition uh on like some sort of small molecule shape or some protein motif or something like that. But if you wanted to condition on something that was sequence based, right, then using protein generator would make a lot of sense, right? So yeah, this is just and like in these cases that I showed today, the intention was to condition on a geometric motif, in which case you would RF diffusion framework makes more sense. But in the case where you want to condition on a sequence motif, protein generator will really do the trick for you.
Okay, so you're saying that for protein generator, you would have to condition on the scaffold plus some plus the identities of the scaffold already, like the residue identities, and you don't want to keep those fixed, the residue identities.
Well, it's not strictly the case, right?
Yeah.
Like you I think in protein generator you also can condition on just geometric motifs, but I think like the power of that method is more for things like, oh, we want these types of sequence features, we want to upweight this type of sequence information, or like things like that, which is like the things they showed in their paper, right? Whereas for RF diffusion, it's more like I have this geometric like or like chemical shape, and I want to like that was kind of how it was optimized over, not thinking about the sequence.
Yeah, but you can also do it with protein generator, and we have reason to believe that protein generator works better. But then what are the results? Does it actually work better for the same application or not? Do you know?
Uh, I I think they're working on kind of adapting some of these things, but I don't know if we have a great head-to-head comparison. Yeah.
Okay, then I don't see any. Yeah, okay, we can go for this question. Ah, no. Did you benchmark PPI prediction of RoseTTAFold All-Atom?
Not not the yeah, no, we haven't.
Okay. And then someone's asking in the chat, why do you, or do you think there might be something useful if we, instead of pre-specifying the number of residues that we want to generate, we sample the number of residues randomly? And I mean, yeah, sure, you can just have a categorical distribution over number of residues and sample that first. Or yeah,
Yeah,
what do you
that's actually how these designs were made in most cases. Like the in the very start, you specify like the exactly what you said, like a categorical distribution over residue lengths, and then it gets sampled right before you do a forward pass.
Many thanks to everyone who came to this session and asked some nice questions and participated in the discussion. And of course, also many thanks to Rohith for the nice discussion. And yeah, we heard it. RFAA diffusion will be out soon, probably still in 2023, and probably also coming with ligand MPNN. So if you want to design your molecules, give it a try. And yeah, you'll probably find that information on Rohith's Twitter if he once he releases it. And if you want to join our future reading group sessions yourself, all the information is down in the description. See you around.